Nitrogen monohydride is a simple compound that has been detected in interstellar space history. One of the earliest papers on the NH molecule was in 1976 by Richard M. Crutcher and William D. Watson. They were still trying to pinpoint the absorption line for NH. There was already theoretical upper limit of 0.3 mA, but they needed a more exact figure. They thought that NH should normally be produced on grains at about the same rate per atom as O and possibly CH. However, its formation by gas phase reactions was extremely slow and could be neglected in comparison with the possible rate for surface reactions. The presence or absence of NH at a certain abundance level could then be interpreted as evidence concerning the importance of surface reactions. Their hope was to find the abundance ratio between NH and O. They weren't able to find the absorption line for NH. Therefore the observations were inconclusive. Interstellar NH was discovered in outer space for the first time in 1991 by D. M. Meyer and K. C. Roth. NH is reported in the diffuse clouds towards eta per and HD 27778 from high-resolution high-S-N spectra of the NHA 3πx3 sigma absorption band, near 3358 A. These observations represent the first detection of this molecule anywhere in the interstellar medium. Shortly after NH's discovery, Wade and Blast, Williams, A. Miller, J. Nadad, and L. A. M. did some work on NH in 1992. They noticed that the observation of NH in the interstellar clouds towards per and HD 27778 could not be explained with conventional gas phase chemistry models. They proposed a non-equilibrium model for the per cloud, which incorporated grain surface production of NH and O would be able to reproduce the abundances of all the observed species accurately. A pure gas phase model and cloud interface model, in which NH and CH+ were formed in a warm and tenuous environment, failed to explain the observed high abundance of CN. Hence, the observations of NH in per and HD 27778 provided evidence for the presence of grain surface reactions leading to molecules other than H2. At the end of their research, they concluded that even though the gas phase formation of NH is given a large rate coefficient, NH was calculated to be underabundant with respect to the observations by a factor of 30. From this they discovered that a cold environment with a temperature of about 30 K favored an efficient production of CN from NH within the diffuse cloud chemistry. Within diffuse clouds, H- plus NNH plus E- is a major formation mechanism. Near chemical equilibrium, important NH formation mechanisms are recombinations of NH2 plus and NH3 plus ions with electrons. Depending on the radiation field in the diffuse cloud, NH2 can also contribute. NH is destroyed in diffuse clouds by photodissociation and photonization. In dense clouds, NH is destroyed by reactions with atomic oxygen and nitrogen. O+ and N+ form O and NH in diffuse clouds. NH is involved in creating N2, O, H, Cn+, CHN, NH2+, NH+ for the interstellar medium. Significance: NH has been reported in the diffuse interstellar medium but not in dense molecular clouds. The purpose for detecting NH is often to get a better estimate of the rotational constants and vibrational levels of NH. It is also needed in order to confirm theoretical data which predicts N and NH abundances in stars which produce N and NH and other stars with left-over trace amounts of N and NH. Using current values for rotational constants and vibrations of NH as well as from O and CH lets us study the CNO abundances without resorting to a full spectrum synthesis with a 3D model atmosphere.